All right, thanks a lot for inviting me to give this talk. This talk is a little bit of an outlier in this workshop, I believe, but I think that that's what makes it even more interesting to some degree. We heard a range of amazing talks that I'm always bedazzled about the creativity of all those interesting devices that are being invented and introduced in computer systems. This talk is about the upper layers, like from, I would say that we're raising from Earth to somewhere close to the sun in terms of, the scale where we are going to talk about. Okay, so I'm going to talk about operating systems and applications. And what I really want all of the attendees to realize that, the technologies that are being talked about these days and at this workshop are going to be really disruptive for the whole part of the operating system application stack, for the software stack in particular. And this disruption will be so significant that it is quite unlikely that we're going to see these technologies being adopted easily, or at least not as easily as we would want to for general purpose computing. And so it raises a very important question that someone can say is pure engineering and someone can say is more research, but I believe that they're kind of interleaved, which is what are we going to do till then, right? What do we need to do and how are we going to survive this stagnating curve of CPU performance? And the answer that we are seeing the industry is giving now, and also researchers as well, is hardware accelerators or hardware specialization and near data accelerators. Right, so basically, this is the curve that we're going to be now on in the foreseeable future until these new exciting technologies get matured and adopted. And it is really important to understand that these technologies that we have heard today and yesterday, they are going to make strides into the systems first as accelerators and only then potentially replacing some of the general purpose computing. So this talk is as relevant for those technologies as it is relevant for the technology that I'm going to talk about today. They're more kind of traditional ones. So, in fact, if we look at the hardware systems today, and again, that's the reason when I'm saying that what we are going to talk now about is like, like a sun from the earth, like what those systems are from transistors, right? We're seeing that more and more computing devices in our normal computers are becoming programmable and they're gaining more and more compute capabilities that usually have not been such, right? So for example, network I/O accelerators, they can run code now. Storage systems can run code, and GPU parallel accelerators apparently can run code, right? So CPU is no longer a central, right, programming unit. It's already yet another programming unit, and all others are the components that allow very efficient operations for a particular type of workloads that leverage those devices. For example, again, for network systems, you would imagine that you would run some kind of network logic on right on the network card. So the interesting thing about it is that it's not only logical to run computation close to data, but it's also extremely appealing for the same very reason that we do not need to move the data. It's already on the move. It's passing through the device, so why don't we compute it there? And it makes a lot of sense to do that, and that's why the industry is going that path. So if we kind of take, again, a very, very kind of very high-level view of this near X devices. And again, I'll go back to that slide and would mention that the kind of term for the system that can allow programmability on all those devices, I would say it's called Omni-programmable systems because they're really programmable all around the hardware stack, not only on CPUs. And for lack of a better term, I will call all those devices near X units, near execution units, NXUs, because again, GPUs already taken, CPUs is taken, so what we are left with, right? NXU. So I will call them NXU for the purpose of this talk. So NXUs are really impressive in terms of the fact that they're basically breaking the memory wall, right? They're already sitting near the data, they don't need to move it all around. Also, they're jumping over power wall. Why is that? Because they basically are separate units. They do not take up the space on CPUs. They're sitting somewhere else, and therefore they're not breaking the power wall, but they're definitely extending the amount of real estate that you have in the machine. But they are building another wall, which is the programmability wall. Okay? And so programmability wall is this #1 problem that we're going to face in the coming systems, and that's exactly what I'm going to talk about. I'm going to talk how to break this wall. And in my talk today, I will try to analyze and give very, very kind of simple example of a very simple workload where we would probably use those kind of systems, those kind of omni-programmable systems to accelerate one, but we would fail to do that efficiently. I will talk about the basic principles of building operating system, which to me seems to be the core or the key component of breaking this programmability wall, with a bunch of examples that we came up with in our group. And I will conclude with the final summary. So to motivate this talk a little bit, we all know that in system design, the more components we add to the system, the higher the complexity becomes. And the complexity raises exponentially because of all the possible permutation of different interactions. And that creates a lot of problems with programming such systems, right? So with more compute elements we add, the higher the programming complexity. And as a result, the number of developers that are capable of taking advantage of those capabilities is dropping dramatically, together with underutilized hardware, together with poor application performance, together with lower efficiency and high cost. So apparently the implication of not being able to program those systems is effectively by not having to even come up with those systems first, right? Because there's no point in building an accelerator that would not accelerate anything. It would be just waste of time. So in order to explain why we are going to see all these effects when we add more processors, let me show to you one very simple example of a server workload. Okay, so this is actually a very common or very standard, I would say, server application used today, for example, in Flickr for storing pictures. So what does it do? Basically, it's a network server that stores pictures. And whenever you upload a picture, it enhances the quality of the picture on the fly and stores it in a disk. And whenever you want to access that data, the picture gets resized to fit the dimensions of the device that you're accessing it through. Okay, so if it's a mobile phone, it will be small. If it's a desktop, it will be large. So how would you build this application given 4 devices, right? You give a NIC network adapter that is programmable, given an SSD, a storage device that is programmable, giving a GPU, apparently programmable as well, and a CPU on the side, okay? And so the natural mapping would be to actually map the parsing, or basically the part that receives the packets from the network and realizes what requests you're actually having. Mapping that to the NIC hardware, to the NIC processing unit. Improving the contrast in GPU and resizing in the SSD, all done inside those devices. For example, for SSD, it's really great to do resizing because sometimes you would retrieve the picture that is, a tiny fraction of the original size, so you would save a lot of bandwidth by doing that inside the SSD itself. And what is really remarkable about this picture is that you don't have CPU in the loop at all. For this particular application, you really do not need CPU as something that would do the computations. So you would imagine the kind of architecture for the program that would look like this. You would have your network device, receiving all the data, and then passing it over to the SSD, doing all the necessary manipulations, resizing, storing the new image, and then basically marshalling the response back. Is this a reasonable architecture, what do you think? So I believe, yes, I have one operating system person here, and he approves. That means that it actually makes sense, okay? But do you think it will happen today? Well, the obvious answer is no, because you still have the CPU in the loop, and the reason why you still have it is because it provides all those nice abstractions that look like where the data does not look like a stream of bits, but actually a stream of network packets or a stream of reliably sent operations and some logic that you can attach to it. And for that, you need real network stack. For that, you need file system. For that, you need all those nice properties that you get for free from the operating system in CPUs. And if you're going to use them, though, what you're going to have is this kind of operation where the data and control will flow around and will ping-pong back and forth, fundamentally losing all the premise of near data computations, because you will not have the computations near data. You will have to really pass them around. Okay? Again, to emphasize, the real reason is that those devices don't understand files and don't understand network streams. They understand bits and they understand blocks. They don't understand the high-level abstraction that we really need. So the root cause for this problem is that in modern systems, the CPU is the root of all operating system logic. It's the only thing that decides where and what is going to be running, as that's the only thing where the real program is running, fundamentally. Okay? So if we get rid of the centralized point of control, we're going to get all the benefits of near-data systems. And that's the point of OmniX. OmniX is an accelerator-centric architecture which builds the operating system that is kind of scattered around all those near-data programmable devices. And it allows you to basically leverage and build the code exactly in the way you would imagine it to be built without the necessity of getting back to the CPU. So I will give you very few, very simple design principles that are behind OmniX with very few examples about how it actually works. So the first principle is that unlike most of the operating system that we know today, the one that we will be using in OmniX is actually single application operating system, meaning that all the services that we would need would run on the devices themselves as a part of the application. That would make it extremely efficient. So I would want to show to you one particular design point for operating system abstractions for GPUs that we have. And here, there are a bunch of challenges. So what is the GPU fundamentally? GPU is the processor that runs dozens of threads, many thousands of threads. Unlike CPUs that run dozens of threads, these are really, really massively parallel. It means that the way you build APIs or abstractions for GPUs are very, very different, right? So you really need to change the semantics of those interfaces. You need to take into account the fact that GPUs do not have shared memory with the CPUs in a way that we used to have in CPUs, and therefore you need to build very specialized locality optimized operating system design. And last but not least, GPUs are really peripheral devices, at least today in their architectures, and that means that you would have to take advantage of some other functionality on both CPU and other peripherals in order to allow GPUs to access them. So one of the examples that we published and which started this whole line of research was the library that allowed GPUs to access files. And what is really remarkable is that in this particular case, this is the example where you take the GPU and make it the first-class citizen in the system, right? Just like any other accelerator should have been. Okay? So in this case, GPUs would be able to access the files just as CPUs would be able to do that today. One of the key aspects of the system is the automatic optimization for locality. So if you look at this picture, you will see that there is the cache that caches the data when it gets into GPU from files. And this is a very standard approach for CPUs. Again, it's never been done for GPUs before us. What is really important here is that this page cache or buffer cache that caches the file data is optimized for the way the GPU works. Okay, so it's highly parallel. It handles tens and hundreds of thousands of requests concurrently, unlike CPU page caches. Another example, very similar in spirit, is the library that allows GPUs to access network. Okay, so here what you can see is that GPU can run just regular server without having to use the CPU. And a GPU native client may access either the server or CPU client, so it's absolutely transparent for the outside world, whether you're running your server on GPU or CPU. But it does allow the expressibility of building regular network servers just on another device. So not only that it is convenient, but it also it does reach the right level of performance. Think about the application that we built, where think about border control that have biometric passport control. Here you present your identity, and they take a picture of you, and then you just pass those into the server, and that matches between your identity and the picture in the server database, right? That's the biometric authorization. Apparently, this is a very computationally intensive operation. It needs to be done reliably and quickly. And what we're showing that with the use of GPUnet, and this is the lower part of the picture. This is the throughput latency curve, the standard one for building servers. What you can see here is that GPUnet is getting us much faster performance, both latency and throughput, and also improves the number of lines of code that you need to write, even compared to the CPU server. Okay? So what it really means is that not only do you gain capabilities of building faster servers, but you also gain them in a way that is convenient for the programmers to take advantage of. Right. Another very important aspect of OmniX is the fact that we are getting rid of the CPU in the loop. You see, there is no CPU at all. And we want to provide the control and data directly to all those devices without passing through the CPU. And this is why it is important. One of the particular examples I want to show, again, touches the GPU and access to the network. So we build a small library that allows the GPU to directly access the network card without going through CPU. And interestingly enough, but kind of expected, we are getting much better latency, basically the 5x latency improvement from using direct access from GPU to the network card versus going through the CPU. Again, it just proves the point that CPU is the bottleneck. But even more interesting fact here is that if we take a GPU server and we build it in order to, we accelerate a certain server and increase the number of GPUs in a server, then it turns out that the CPU-driven design, the regular one, just goes and flattens out in terms of its scalability with the number of GPUs, just about 8 GPUs, okay, in this particular workload. Again, this workload is pretty common in, for example, Google image search. Okay, so already with 8 GPUs, it's not worth adding more GPUs to the server in order to improve the performance of this application. With our design that does not use any CPU in order to run it, we can reach up to a factor of 15 on 16 GPUs. Again, what it really points, the main point of this slide is not to say, GPUs is the way to go. The real point of this slide is to say that CPU is not the way to go, okay? You do not want to use the CPU in order to control all the accelerators. Otherwise, you ruin all the benefits of all those accelerators. So now I'm going to touch on the ongoing effort that is basically computing inside the network card. And this is a very important part of our work now, where we are trying to build modern accelerators for data centers, where we can build network services that have low predictable latency, that work without depending on memory bandwidth between the network card and the CPU, improve the power efficiency, and basically free the CPU and the caches from being polluted by the traffic that is coming in from the network. Okay? How are we going to do that? Actually, there is hardware that does just that, at least on the paper. Now go and develop something with it. That's the separate question, and that's exactly the question that we are addressing here. So this is a real piece of hardware from Mellanox. It's called a Innova network card. It has an FPGA right on the card, right on the network card, and here the data comes in, goes through FPGA, okay, goes to the network adapter, and finally ends up being in CPU. Okay, that means that basically as the data flows in or out of the machine, we can do the processing on the fly without having to store the intermediate data in any memory buffer, and by that improving performance substantially. So one interesting application, really simple just to understand the basic principle. What can we do with this kind of thing, right? We can do filtering, for example. What it means is that if you have zillions of sensors that send data all over and to a certain server, we can accumulate all the data without passing it to CPU For example, if it's a temperature sensor, we want to trigger only if temperature rises beyond a certain bar. And so in that case, all the network information would be accumulated inside the network card itself, passing the data further to the CPU only in case where it is necessary to trigger some alert. Okay? So CPU is used, but it is used for rare events. Now, what we built is the framework and programming model that allows us to actually take any application, not particularly this simple application that I described here, and to allow anyone to use this kind of hardware without the complication that we are experiencing in these very days in order to build. Basically, we're building a new operating system for this card. So how it really works, really, really quick. So this is what we call shell or sandbox. This is something that runs any user code that we need. And we build ours inside this shell, okay? So the data comes in over here, gets into this small app that we install. We call it iKernel. And then on the other side, there is a host operating system with all the network stack adapted to use this whenever necessary, right? So then let me show you what happens if you have multiple applications. Then this very sandbox is going to do all the switching and do all the necessary manipulations. Now, a little bit more complicated application that just to show that the same principle and the same framework would easily work with our mechanisms. Think about tweet sentiment analysis. Turns out that in Europe now, Twitter, Google, and Facebook are facing really significant regulatory constraints to inhibit hatred and any kind of problematic statements on their social media. So they really have to filter all those things. And for example, Twitter sentiment analysis is one of those tools that might be potentially used in order to filter all the hatred from Twitter. So how would you build this kind of thing on our hardware? You would build an approximate classifier that would just pass through anything that it cannot classify, but basically return the results immediately if it knows how to classify that. And so here how it would work. So for example, you have a statement that goes in and says, I love you. Okay, apparently it's okay to pass it through. And so the response would be immediate directly from the network card without passing it further. On the other hand, if you have something else that looks like Memristor, right? So there's no point in NICA to recognize this word because it's quite unlikely to see that on Twitter. So the approximate classifier would fail to recognize it and it would pass it to the host operating system that would have the right classifier saying that it's an absolutely benign word. It cannot be used for hatred, apparently. Okay, so it will be returned back happily. So as you can see, this framework is very versatile, and basically this whole idea of running some of the computation on NIC actually makes sense. So no systems work is valid without showing a reasonable graph of performance. So let me tell you, this graph is not reasonable for now, but because it's really like hot yesterday from the oven, right? But already what we're seeing here is we have 10x performance improvement over CPU for the type of workload where we don't pass anything to CPU. So everything is being handled by the network card. That is great. There is a slight little problem over here where we get behind, but that's exactly the work in progress, right? What is really important, though, that besides this 10x performance speedup, we also get about 5x on top of that with power efficiency. That is even more important for data centers. So I'm almost done, but I can't finish my talk without saying that we don't need the CPU, apparently. Okay, so you already realized we don't need it. Well, that's not really true. We don't want to be completely incompatible. So we ran the basic skeleton of the program on CPU, but the real kind of heavy weighting of the compute logic, of software logic of the application is run and managed by the accelerators themselves. So this is a huge project. OmniX is a multifaceted kind of effort, having many people working on it. And as you can see, most of them are pretty happy, despite working on pretty challenging topic. So I want to finish and say that it's been my great pleasure to present this work here. I do want it was a little bit thought-provoking because building all those devices is really cool. It's the future, but it's the future that we need to jump into, and this is the bridge over that gap. So with that, I would be happy to take questions.